Hello all, welcome to this video on Microprocessor Lab. Today I'll be talking about stepper motor interfacing with 8086. Now every motor converts power. Electric motors convert electricity into motion. Stepper motors convert electricity into rotation. It can be very accurately controlled in terms of how far it will rotate and how fast. Stepper motors are named so because each pulse of electricity turns the motor one step. Stepper motors are controlled by a driver which sends the pulses into the motor, causing it to turn. The number of pulses the motor turns is equal to the number of pulses fed into the driver. Motor will spin at a rate that is equal to the frequency of those same pulses. Stepper motors have a stationary part, which is the stator, and a moving part, which is the rotor. On the stator, there are teeth on which coils are wired, while the rotor is either a permanent magnet or a variable reluctance iron core. Each winding is connected to the winding of the opposite pole so that both poles are magnetized in the same polarity when the current is sent through the pair of windings. The opposing pairs of poles constitute one phase. Here we have a three-phase motor. Now looking into the different types of stepper motors, we have permanent magnet motor, variable reluctance motor, and a hybrid motor. Stepper motors are designed based on the principles of electromagnetic theory in order to make a motor turn a precise distance when a pulse of electric current is applied. The center tap on the stator winding allows the current in the coil to change direction when the windings are grounded. Stepper motors are used in applications like computing, robotics, cameras, scanners, 3D printers, fluid control systems, and in equipment for accurate placement. Now let us look into the working of a stepper motor. Here I will consider a stepper motor, which is a two-phase full step sequence motor. Now in the full step sequence, two coils are energized at the same time and the rotor will rotate accordingly. Now this is an example which is labeled as A, B, C and D, and these are the four poles and this is the rotor. We can see that the opposite poles are connected so that when the current is applied here, it will have the same polarity. The same for C and D. In some other references, you may see that instead of this, the labeling can be like A dash, B dash, or A1, B1, A2, B2. Now first I'll choose the two poles A and C for applying current and let us see how the rotor will shift. Now when applying current at A and C, we'll see that the pole A is polarized as north-south. It will be the same for B, north and south. In case of C, it will be north-south, the same for D. These two south poles will attract this north pole and these north poles attract this south pole, as a result of which the rotor will shift like this. We make a table entry here where we show at a particular instance the poles where we apply the current. Those will be labeled as 1 and the others will be labeled as 0. Now we choose the next poles, which is C and B, and let us see what all changes will happen there. We can see that in case of C, the polarity will not change, but in case of B, it will be reversed. So this will be north-south, north-south. These south poles will attract this north pole and these north poles will attract this south pole. And we make the corresponding entry in the table where B and C will be 1 and the other two will be 0. We can see that the rotor will shift like this. Now choosing the next pair of poles to apply current, we choose B and D. We make the entry where B and D are 1 and the others are 0. Now these south poles will attract this north pole and these north poles will attract the south pole and the rotor will shift like this. And for the last pair, we choose A and D, which will be 1 and the other 0. The polarity will be same for D, but it will be reversed for A. North-south, north-south. These north poles will attract the south pole and these south poles will attract this north pole, as a result of which the rotor will shift like this. Now we have written the hexadecimal equivalent for all these 4 entries. Now this will be the data that we are feeding into the stepper motor in order to perform the stepwise motion. We saw that a complete rotation here took only 4 steps, which means the step angle was 360 degree divided by 4, which is 90. Now we look into a stepper motor control. So it is a compact integrated IC. A stepper motor may run at voltages varying from 5 volt to 12 volt, and similarly the current drawn will be somewhere in the range 100 milliampere to 400 milliampere. The supply will give the motor specifications. So accordingly we must design the supply. The power must be regulated so that the fluctuations in the speed and torque may be avoided. So in this circuit we will be using 4 2N6 silicon PNP power transistors, which are used usually in power amplifiers and switching circuits. Now this is the stepper motor controller circuit. Now here we have the circuit diagram, and comparing with this we see that there are 4 connections: CN2, CN1, CN3 and CN4. Now this is CN2, CN1, CN3 and CN4. Now these 4, U1, U2, U3, U4 are the PNP transistors we talked about before. In the diagram, they are these. And this is the circuit. And in case of CN2, this connection, it has 5 volt, 12 volt, ground and now connection. Now the other end of this cable is connected to the corresponding port in the 8086 trainer kit. Now looking into CN1, this is a bus connecting the controller to corresponding pin in 8086 trainer kit. Now CN3 is not used here. We are concerned about CN4. Now that is the connection through which the data is fed into the controller. So here we have 6 connections, 2 grounds, and then we have PA1, PA2, PA0 and PA3. These values were the ones we derived in the tables when we saw the working of a stepper motor. Now the other end of this cable is connected to the motor, through which these values are communicated for its stepwise rotation. A few other details on the motor that we are using here. In the example I have shown before, we saw that the step angle was 90 degree. In the demo that we see here, we see that the step angle of the motor is 1.8 degree. So on calculation we see that for one complete rotation we need 200 steps. Also the acceleration and deceleration can be from 1000 to 3000 steps per second. And this motor is interfaced to 8086 with the help of an IC 8255, which is the programmable peripheral interface. Now 8255 has 8 pins, which are called PA0 to PA7, which are 8-bit bidirectional IO pins that are used to send data to output from a device and to receive data from an input device. Here we are only using the lowest significant byte, which is PA0 to PA3 of port A. This is the same table. We have labeled it according to the ports of 8255, and this is the data. That is the hex equivalent of this. Now this PA0 to PA3 is connected through buffer and driving circuit to the winding of the stepper motor. This was what I talked about previously. This is connected to the motor. A delay routine is used here to generate a delay between the steps. This delay can be changed to make the steps faster. The minimum delay depends upon the maximum speed of the stepper motor, which is specified in the specifications. Now talking about 8255, It has two modes of operation, which is BSR mode, which is bit set reset mode, and IO mode, also known as input output mode. Now this mode is determined by the control word register, and in the program we will be seeing this control word will be stored at the location 46H. The control word value will be 00 if it is BSR mode and 80 if it is IO mode. Now this stepper motor is an IO device, so the control word should be 80. As we already saw, we have 4 poles which are A, B, C and D, and those 4 data we have seen. It will rotate the motor in a particular direction, and in order to see the opposite rotation, we need to feed the data in the reverse order. So after taking each data, we will out that particular data to the IO port of 8255. So in this program, that value will be 40. Since we have already seen the steps that are involved in the interfacing, it will be easier to go through the program. So in the beginning, we have to start by setting the control word. Now this program is written in the location 0400. Since it is an IO mode, the value is 80. Now AL is the default register that is used to out to a particular port. So I'll write this value 80 to AL and then place the value at AL to 46, which is the location of the control word. Both these instructions are 2 bytes each. Next, we'll load the value 4 to the counter register, lower byte CL. Since the number of steps will be 4. Now this is a 2 byte instruction. Next, we'll take values, that is the data we obtained by deriving it from the table, at the location 0500. So the 4 values will be stored starting from 0500 and each value will be loaded to VX. Now this is a 3 byte instruction. Then that value is loaded to AL, which is a 2 byte instruction. And each of these values, as we saw before, will be out to the IO port of 8255. So out 40, AL. This is also a 2 byte instruction. Next step is to call the delay. That is to generate a delay between each step. Now the delay code is written at location 0415. So we'll move on to that location. So here we see that we push the value of CX. So we are actually saving the value of CX. This is a 1 byte instruction. Then we load CX with the maximum possible value, which is FFF. Now this is a 3 byte instruction. Next, what we do is we'll loop in this same location, the 0419. And each time we loop, the CX value will be deducted by 1. And this happens to loop until the value of CX is not 0. And when the value of CX is 0, that is when the delay is completed, we'll pop out the value from CX. That is the actual count, the number of steps which we loaded in CL in the beginning. This is also a 2 byte instruction. This is a single byte instruction. Now RET is a return. It will return to the location where the call happened. This is also a single byte instruction. Now we'll go back to the location which was this. Now we have taken one value, generated the delay. Now we go for the next value for which we need to increment BX, that is to location 0501. Now this is a single byte instruction. Next, we'll loop to the location 0409. What we do is we'll be moving it to AL, putting it on the IO port of 8255 and generating the delay again. Now this will be repeated for each of the steps. This will continue, and after that we'll jump to 0404 where we'll reload the value of CL again. Because each time You see this, it will go in an infinite loop until you press the reset button of the microprocessor training kit. The stepper keeps on moving. The motor keeps on moving steps. That's why this program keeps on running. And that is the end of the program. Now, for one set of rotation, I'll feed these values in these particular locations. Now, to see the rotation in the opposite direction, the values will be reversed and stored in the same locations. One more thing to highlight is what I said, I'll be repeating it again. In this diagram, we said that after discussion, we saw that within 4 steps, you could complete a single rotation and the step angle was 90 degree. So the case we are going to see, we have step angle as 1.8 degree. So note that these 4 steps will keep on repeating. And we know that the motor we are going to see have total number of steps as 200. So here it took 4 steps to complete one rotation. In the motor we are going to see, it will take 200 steps for one complete rotation, and each step will move by an angle 1.8 degree and it's not 90 degree. Please note that. Now we look into a demo of how this interfacing is done. So this is the connection. As you can see, this was the bus connection. This is the connection 2. This bus connection, this connection 2, and this is the connection to the motor. And this is the part that I will be focusing on. As it moves, we can detect each step motion. Now, as in the usual case, we will be writing this program to the particular location 0400, starting by setting the control word register. And putting into the location 46H where we have our control word, setting the counter as 4, as we are repeating this set of 4 steps in an infinite loop. Then we are loading the address where we will be feeding the data, which is 0500 to BX, and then we access the value from the location of BX to AL, and we take each of these values and place them in the output IO port of 8255. Then in this step we are calling the delay. So after the delay is generated, we'll increment BX to access the next value. Then we'll perform a looping to the location 0409 and a jump to 0404. where we'll take the count again as 4. So in the delay program, we'll push the value of CX. Then we load CX with double F, which is the max value. Then we perform a loop in the same step. That is the delay that is generated between the consecutive steps. Then after the delay, we pop out the value of CX and we returning from the call. Now loading the values at 0500, which is 0A, 06, 05 and 09. Then we'll run the program. We can see that it is moving in the anti-clockwise direction in this example. Now, in order to do it in the clockwise direction, we need to reverse the order of the data we gave before. So, we go to the location 0500 and load the values in reverse order. So, we'll start with 09, 05, 06 and 08. and on running it, we'll see that the motor is rotating in the opposite direction. For our case, it is clockwise direction. That's all for now. Thank you for watching.